Thanks a lot for being here. My name is Nico, and my presentation today is going to be about a set of tools that go beyond the usual optimizing compilers, right? Everybody knows about GCC02, GCC03, and how they basically generate optimized machine code starting from your source code. And today, we're going to be talking about an additional set of complementary tools that modern compilers offer that can make our code even faster. They're called link time optimization, LTO, and FDO, feedback-driven optimization. And during the presentation, we're going to see what this means. Thanks a lot for our sponsors. I think you've already seen this. OK. As I said, we're mostly going to be focusing about performance today. I'm not a compiler engineer, right? I work for Cruise Automation at San Francisco. We build self-driving cars, and I pretty much basically handle the tool chain, the build system, and that sort of stuff, basically helping engineers write performant code. And so I was like, yeah, you browse the internet, and you see stuff like Firefox is now built with Clang, sizable performance wins, and I'm like, oh, maybe I need to learn something about this. Maybe I can improve the performance of our code without actually having to change our code. And that's why I started looking into this set of technologies. As a note, I'll be mostly jumping around GCC and Clang during the presentation. I'm mostly familiar with Clang because that's what we use at work, but the basic concepts apply to both major compilers. So let's get started. This is what we call the separate compilation model for C and C++. You start from the top here with your source code, and then you run your source code through the optimizer, code generation, and you produce an object file. And you can do this for each of the CPP files that make up your project. Finally, you run all the object files through the linker to produce the final executable. So is everybody familiar with how this thing works? Can you raise your hand if you're not familiar with how this works? OK. So yeah, the main idea is that your compiler looks at each of the source code files independently, and then basically generates an object file that contains the machine code function by function, basically. And then what the linker does is that it looks at all the object files, matches up function calls in one object file with function calls in the other object file. For example, you can have a function A in this object file and a function B in this object file, and they might be calling each other, right? The link makes sure that all of these dependencies between the object files match up correctly, then does a bunch of magic with the addressing stuff, and finally produces the final executable. OK, so let's move on this. So this model is great, right? It's basically we inherited C++ inherited from C back in the 70s, right? Where computers were so limited that preparing all the source code for even just loading up the source code for the complete program in memory was basically impossible, right? So they had to do this trick where they split everything up in separate files and then do a simpler step at the end. But this is great even today because programs have gotten so much larger that even being parallel helps, right? We can use more CPUs to compile large programs without basically taking ages. And the other cool thing about this, as you all know, that compilation of a big project can be incremental in the sense that if you change a typo in a single file, you only need to recompile that file and then link without having to recompile everything else. So what's the problem here? So far, so good. This seems to work great. So let's start with some stupid code. So we take this stupid code that just runs a loop a billion times, but the loop actually does nothing because the function does nothing. We compile it, and I think I posted. So we compile it as usual, and it takes 0 seconds to run, right? Even if we're running the loop a billion times, that's not surprising, right? Is this surprising? OK, cool. So what happens is that the compiler inlines the function. The function does nothing, so basically the loop itself does nothing. OK, So what we do here is we want to be tidy, right? So we split up our code into a library that we call lib.cc, where we move the implementation for the function. We move the declaration for the function in an header file. We import the header file in the main entry point for the function, and we do the same. So what happens now? What do you expect that should happen now? Is it going to run faster, the same speed? OK, cool. And indeed, it runs much slower. So the code actually runs now, right? So it takes like 1 second, which is OK. I have like a 2 gigahertz CPU, like runs a billion iterations, sort of matches up, right? So is this surprising? No, right? OK, cool. And so basically, what's happening here is that the compiler can see the function implementation in the CPP file, because as we said earlier, each translation unit is compiled independently, right? So the compiler can't inline the function code anymore. It cannot replace the body of the function inside the for loop, because it can only see the definition of the function, not the declaration. And so this is pretty bad, right? Because inlining is basically the secret sauce that makes modern C++ work. That's basically the secret sauce that guarantees that we can have zero-cost abstractions, as basically all our tidy object-oriented code actually gets desugared away, and the machine code is basically has no overhead. And more specifically, inlining is great both directly and indirectly, right? Of course, no function call means that we don't need to set up the stack, we don't need to call the function, we don't need to return the function, and we don't need to basically clobber up the registers for passing the arguments and return values. But actually, like, some of the most important overall benefits of inlining come from the fact that we're giving the optimizer more code to work with, right? So by replacing the implementation of the function instead of the function call, the optimizer has more context about the implementation it can do, right? So for example, it can do constant propagation across the caller function and the callee function. And this is stuff you can't do if you have an opaque function call with arguments, right? Because the compiler can't see beyond the function call. On the other hand, you can't really inline everything, right? If you inline everything, what happens is that your code size blows up. So both in compilation time and in binary size. And the problem with like bloating up the binary size is that you're filling up your CPU instruction caches, right? And so overall, you might even like decrease your performance. OK, so what happens? We're not really happy with the situation here, right? So what we do is we had a magic flag. We had an FLTO magic flag to our GCC or Clang invocation. And what it does is this restores the performance we had earlier. Basically, optimizes everything out again. And this is the magic of link time optimization. So, any questions so far? Cool. So what does link time optimization actually do? Instead of, this is similar, the first chunk from the top is similar to what we had before, right? We take each individual source file, but we don't generate the machine code. We actually stop at an intermediate representation of the machine code. So this I called LL files, which is, for example, the intermediate representation that's used by LLVM throughout the compilation process. And what we do here is that instead of generating machine code and creating object files for each translation unit, we stop, we save the intermediate representation, and then we link all of the intermediate, we basically group all the intermediate representations together, and then we pass them to an optimizer and generate the machine code for the final executable. So the cool thing about this is that by the time you get here, you have visibility about the intermediate representation of all the functions. So another way to look at it is that you could basically sort of works the same as like concatenating all the source files, but not really. This is better for like a few reasons we're going to see later. So basically what happens here is that we're generating all the code, which seems great. If you do something like this, we call this basically conventional or like monolithic LTO. which was basically the simplest way you can do LTO in practice. And in fact, it was implemented in like the GCC and Clang since the early 2000s. However, like this simple model has a bunch of problems for everyday development. First of all, like as you can see in the graph, a lot of work, like the actual like heavy work, heavy duty work, is done serially. Because this step is going to be pretty fast because you're only running some preliminary optimizations here, but then the heavy duty work is done here. And as you can see, this work here is serial. So you're looking at the complete program at one time, which is great because you can do all your optimizations and your relining, but also means that you're basically serializing a bunch of work, which doesn't work on large applications, right? And the other, related to this, the other problem is the monolithic LTO build is not going to be incremental. Even if you change a single file, you basically have to optimize the whole program again, starting from the intermediate representation, which basically is pretty expensive. You need to convert all the intermediate representations to the machine code. You need to do your register allocations. You need to do your inline decisions. So it's basically, it's like a good chunk of the work that like a compiler does. And you need to do it over and over again every time you change a single file. On top of that, the intermediate representation takes up a lot of memory. So basically, this limits in the size of the program you can compile using LTO. And that's why, because these are like a few of the reasons why LTO really never picked up a lot of steam outside of like specialized high performance applications. Because even in like general purpose C++ applications like browser or stuff like that, you would need like 40 gigs of memory just to link Firefox, which is sort of inconvenient. And that basically motivates like a better solution, which is some sort of like at least semi-parallel LTO. So this slide, basically this idea, is taken from the Clang thin LTO project, which is basically a project that Google came up with to basically adapt and like remove the drawbacks of conventional LTO so that they could apply it to their basically in-house software, which is pretty huge. So this is pretty complex, so we're gonna work step by step. We still start by generating the intermediate representation for each file, and this is okay because we can do it in parallel again. And then there's this new step here that's called thin link, which is basically some sort of like indexing process for each of these intermediate representation. Basically, it's gonna look through all the intermediate files and create an index of like each of the functions that are defined in the translation unit, plus some metadata. For example, if you think about inlining decisions, right? Good metadata that you could use, for example, is the size of the function. Because that metadata later will help you decide whether you want to inline the function or not. So for each file, we create basically a sidecar, like an index sidecar for each intermediate file. And then we feed all of this stuff here over to the linker, right? And what happens is that as you're optimizing, say, you still have a main module that you're optimizing, right? A main CC file that you're optimizing. And this is the crucial part. This allows thin LTO to go in parallel even for the final code generation, which is great because what it allows it to like reduce memory use and increase compilation speed. But how do you inline then? You inline by having each optimization and machine code generation step for each of the translation unit, look at the index files for the other translation units, and look up the functions that are called here. So say this intermediate representation calls a function foo that's defined in A. You wouldn't pull the whole A in, that's too expensive. Instead, you would look at the index file, figure out some metadata about A, use some heuristics to decide if I want to align foo or not. And if I want to align foo, I can stream the relevant chunk of the intermediate representation, bring it in my optimization and code generation pipeline, and finally proceed as normal. So basically, each on the independent translation unit can pull other function definitions as needed, but they can still proceed in parallel, which is basically what we wanted all along. And the main intuition behind this is that when you're compiling like each of the translation units, you probably don't need complete visibility into all the other functions in the program, right? Because your inline candidates are going to be like few, like relatively few, right? It's going to be a few % of the total functions in the program. And this means we can go in parallel, and yeah, that's pretty much it for this. Oh, yes, another thing. So I kind of described how the Clang thin LTO model works, which is sort of like the latest and greatest in this sort of stuff. GCC has a similar implementation that's called Whopper, which also is based on the idea of doing as little work in serial as possible and try to do as much as possible in a parallel way. They're pretty much both based on the same concept. Just thin LTO is like a bit newer. So let's recap what we learned about LTO. So basically it allows us to sort of overcome the limitations of the separate compilation model of C and C++. The simplest way, which is monolithic LTO, doesn't really scale to large projects because it basically tries to do most of the work in serial at the end of the compilation job for the whole program, so it doesn't really work well in practice. And there are basically both GCC and Clang have parallel LTO frameworks that basically try to reduce the overhead in terms of memory and compilation time. Okay, this concludes the first part. Any questions? Cool. Okay, so on to the second part of this talk, which is basically sort of complementary to what we just said. We're going to be talking about either FDO or PGO, depends on the acronym you prefer. One is feedback-directed optimization. The other one is profile-guided optimization, and they're pretty much the same thing. So let's jump back to inlining. So as you remember, I keep like beating on this because it's like probably the most important optimizations that modern compilers can do. So like usually what happens like in most compilers is that the compiler authors have some finely tuned heuristics about whether to inline or not, right? Is the function less than 10 lines? Does the function use less than n variables and stuff like that? And all of this stuff is like I mean, you can tell it's like not optimal, right? It's just a bunch of rule of thumbs. So we want to do better, right? And in fact, the idea behind profile-guided optimization is to do better by tracing what the program actually does at runtime when it processes its usual inputs, and then use that information that you gain from the profile and give it to the compiler so that it can make better optimization decisions. So for example, there's like, we already talked about inlining functions. If like a function is frequently called from another function, it might be a good candidate for inlining. Loop unrolling is sort of the same, right? You have some heuristics for like how to unroll loops for optimum performance, basically how to copy and paste the code to reduce the loop overhead. And of course, basically, using the profiles can basically reduce the reliance on heuristics that you have for these optimizations. If you have something like a branch, and the profile tells you which side of the branch is hotter than the other branch, the compiler can optimize the code layout so that basically in the hot path, the CPU just goes through a straight path and doesn't have to jump around, so that cache locality is optimized, basically. So how does the PGO or FDO work in practice? It's a bit of a pain, actually, because you need to build two binaries, not just one. First, you take your source code, you add a flag to the compiler, and this becomes your instrumented build. So basically, the compiler is going to add additional calls that are basically going to generate the profile. They're going to trace which branch you're going to take, which function calls you make, and stuff like that. And this is your instrumented build. Sadly, the added instrumentation code makes it so this program, the instrumented build, runs like 20-30% slower than your production build. So the problem is you can't really use it in production for anything sensitive because you're going to waste either money or latency. So what you do is that you run the instrumented build using representative inputs that kind of match what you have in real life. And this will produce your profile file, which is going to trace like which branches you take, which functions call you make, even like behind the virtual calls and stuff like that. And then again, you take your source code, you take your profile, you feed both to the compiler with a different magic flag, and you finally get your production build. And this is, this is like a bit of a pain in the sense that you need to integrate it with your build system, and you need to make sure that the profiles that you have match reasonable use cases that you have in production. Otherwise, you might even like decrease your performance if the profile is not good. But otherwise, it's like pretty straightforward. It's like one flag here, one flag there, and just make sure the profile matches. So what does PGO get you? Lots of things, but for like our discussion about inlining, the most important output is like a form of a call graph, like a dynamic call graph. This I just stole from the internet, so this is just a bunch of random functions. And it's like a graph, and each node in the graph is actually a function definition in your code. Each edge from one function to the other represents a function call. And then what you do is that you annotate each edge with the percentage of time that the function is called from the other function. So for example, these two functions are like pretty evenly split. This guy, yeah, there are no great examples. For example, this function was basically called 99% of the time from the other functions, right? And this is basically, you can get this graph either by using CallGrind, which is part of the Valgrind suite, and then you open it up with like a tool that's called kCachegrind, or you can use perf, which is like a sampling tool that comes with the Linux kernel, and it basically prints out like a bunch of text, basically prints out like a text form of this, and then there's a bunch of scripts floating around on the internet that take the text format and spit out the nice plot. The nice thing about this is that you could do the same just by looking at the source code, right? You can just look at the source code and figure out which functions are called by other function. But this breaks down pretty easily, right? If you have an indirect call through a function pointer, or if you have virtual calls, you never know which function you're going to call until you get to runtime, right? Whereas if you actually look at where the program is going, you can have like accurate numbers for this. And the cool thing is you put all of this together, and we go back to LTO, and you go back to, you basically take your PGO knowledge and we take our LTO knowledge, you put it together and it becomes LiPo, which is like a thing that a Google team invented in 2010. And the idea is, if you look at the call graph, right, it gives you a lot of information about hot calls, right, about which functions you want to inline. For example, maybe you want to inline this function from this other function, and the higher is the percentage and the number of calls on the edges, that means that those functions should probably be optimized together. And the insight between LiPo is that instead of doing LTO in the way that I just explained, you can actually just not save the intermediate representation at all, just run the program through the profiler, get the profile data, look at the call graph, figure out which functions have hot edges, and then basically reorganize all the modules in your program so that the hot functions stick together in the same module and they're optimized together. And so this was like a way that they managed to have parallel interprocedural optimization, so basically parallel LTO, without actually having to do all the serial work. So before like thin LTO came along, it was like a relatively scalable way of doing intermodular optimization. And so this is probably not, I don't think nobody uses LiPo anymore, given that all the new stuff that has come out since. But I thought this was like a pretty cool idea and good application. I want to conclude sort of like the theory part by talking about auto FDO. So before I lied, right? I told you if you go back to this, I told you that you had to build twice, which is like a big pain. But that's actually not true. I lied. So you can use AutoFDO, which is another Google project. They release a lot of open source compiler stuff, which is great. Instead, what you do is, instead of doing an instrumented build, you use the hardware counters in the CPU to actually have a slightly rougher but still effective trace of what the compiler is doing at runtime. So basically, you use this tool that's called perf, which basically comes with the Linux kernel. Basically, uses the Linux kernel APIs to talk to the hardware counters in the CPU, and you get basically, instead of an instrumented build, you basically get samples. And of course, as any sample-based tool, it's not going to be 100% accurate, but it's basically going to be good enough to give you a good profile. And the cool thing about this is that the runtime overhead is pretty small, so it's going to be like in single-digit %, which means that you can think about running this in production, which gives you the, first of all, you don't need to handle the instrumented builds, non-instrumented builds, and blah, 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 which is a pain. And you can also think about running this in production since the performance overhead is so small. And then at the end, you still do the same. You pass the profile that you generate over to Clang when you rebuild your source code, basically, using the profile data. But the cool thing is you don't need to do anything for the initial build. There's no instrumentation code here. You can take like an off-the-shelf binary and just run it under perf. Any questions? Sorry, I didn't understand what you said.
You can optimize with -2, also the first profile.
Yeah, usually it's better, right? Because you want the hot points in your profile to actually match what you run in production, right? So let's say, for example, if you don't optimize, the compiler doesn't do any loop unrolling, doesn't do any inlining and stuff like that. So the hot points and the slow parts that you see in the profile are basically useless, right? They're not going to match what actually the slow points are going to be, the hot points are going to be in the program, right? So you sort of want your profile to match your production use as much as possible, which also means having pretty much the same machine code if possible. Make sense?
I was just thinking that if it does some optimization at the beginning, we discuss some inline possibilities.
Yeah, I mean, well, this also makes sense, right? For example, what people complain about is that they do this profile guided optimization once, and then they want to do it again, so they want to profile the optimized code already. Now a lot of the sort of runtime behavior of the code has changed, and the second time around might actually be worse than the first time around. So there's a bunch of stuff, but generally you probably don't want to run this with like 01 because it doesn't really make sense. It's going to be, I mean, the machine code you run is going to be so much different from with all the inlining and stuff, is going to be so much different from the profile that doesn't really work out. So I ran some numbers. I can't really show you my company code or anything like that. So I went around and looked from some open source code that had all this stuff already set up. There's a super nice LLVM test suite which has all of the LTO stuff already configured. So actually testing it is pretty easy. You need to build a new, nicer linker, basically gold, with plugin support, because like most Ubuntu distributions don't have it, and like it's super slow, doesn't really work. Once you build the linker, you want to build the Clang, and you also want to build the linker plugin that's used for LTO, which is not part of the default distribution. You pass it the include directories to the bin-util, so you can actually build it. And now you can build the Clang benchmark suite, which is pretty nice because it has some small benchmarks, some large benchmarks, some like simulations of like large applications. And then you can basically run it. I think, for example, if you compare linking time for O3 versus the thin LTO, like a cool thing is, yeah, you basically pick, they have like predefined configurations. So you can pick, for example, an LTO configuration, a thin LTO configuration, and so on. And basically it just takes like a few minutes to build, and you can try. You have to use the LLVM binutils, though. Like basically, they need to be able to read the LLVM intermediate representation. For example, just by like changing a line, I got like almost 3% with LTO and like a bit over 2 with thin LTO, which is nice. And actual programs are going to be way better than this because these benchmarks are like pretty small, so you can't really do anything. I copied this from, I haven't bothered like setting up GCC for this talk. I copied this slide from the thin LTO presentation, where they're like, even if thin LTO is pretty much the same as GCC Whopper, thin LTO is better, go figure. Another cool application of this sort of technology is that it helps you save space, because you can more efficiently prune out unused functions throughout the whole program. And this saves around 22% in the size of the Linux kernel if you build it using LTO. It's better than just pruning unused variables. So thanks a lot for the questions. If you want to reach out, you can find contact info on my personal website. And yeah, thanks a lot again. Oh, sorry. Sorry, guys, I'll do a selfie too. Do you mind? Nice. Looks cool. Any questions, by the way?
Imagine you're a library developer. You need to ensure binary compatibility for your library. Use these techniques.
Oh, that's a nice question. Let me think. I mean, not necessarily, right? You're going to have your sort of public ABI, and then you stick to that. You don't, basically what you're going to do is you're going to hide all of your symbols, right? Except from, you're going to ship like a shared library probably, right? And you're probably going to use a linker script to like hide all the symbols that the users don't care about. And as long as you don't do anything fancy on those symbols, which are going to be the entry point to the library, then anything else that you do, it's going to be your business, I think. So I'm pretty sure you can do it. There's going to be some linker involved, linker magic involved. But I mean, anything that's not part of your public ABI, like users don't care about, right? You're not going to be lining out the public interface. Yeah, but I mean, you're going to have like a public interface, and then your public interface is going to do the actual work into basically private functions, right? And even if the private functions are like inlined or not inlined, the public interface is going to be the same, right? That's what you don't want to break. So as long as you don't break that, it's the same as like switching the optimization flags on the compiler, right? You can definitely ship a shared library that has like different optimization levels with the same ABI for end users. I'm not really an expert. I just build stuff that runs on like a single thing. So I'm not super an expert on like these compatibility issues.
When you use a
yeah, sure. The traces.
If you use the frame pointer version,
Okay.
the inlined codes are not shown in this model. So how profile guided optimization can work?
This stuff usually works.
Because there is no frame pointer.
Oh yeah, we usually build all of our stuff. I think we do some no omit frame pointer magic somewhere.
Inlining codes does it have both the debugging symbols? No, debugging symbols are contained but not the frame pointer. So I think that you should use the word code ref, but it would slow down your code somehow. So it's not easy.
Yeah, that's why you build debug symbols in your perf runners, right? So that you get the dwarf stuff to run. Yeah, but the overhead is not going to be great, right? I mean, I haven't seen like a big slowdown. Okay, no, I mean, I'm sure it's going to be slower, but I mean, it seems okay, to be honest. I mean, you don't run it on the actual sort of production device, but it's okay. Cool. Thanks a lot, guys.